Hi, it's my pleasure to present to you the PHOTONFOOD project. The aim of the PHOTONFOOD project is to develop infrared sensing devices to detect contaminants in food. Contaminants as they are toxins produced by fungi, pesticides or other contaminants that are harmful for human health. We're working closely together with industries and businesses to exploit this technology already during the project and after the project period. So please have a look together with me now at the PHOTONFOOD technologies and how partners work closely together to get this done.
So the coming 3 weeks, we will be trying to integrate all the devices that have been so far made in the PHOTONFOOD consortium here at Wageningen University and Research in the Netherlands.
Hello, my name is Stefan Freitag. I'm a postdoctoral researcher from the University of Natural Resources and Life Sciences, Vienna, from the Institute of Bioanalytics and Agrometabolomics. Our role in the PHOTONFOOD project is to validate and demonstrate that all these developments within the project are fit for its purpose. This includes reference analysis with LC-MS or providing the consortium with naturally contaminated samples to prove that their developments really work with real-life samples.
Hello, my name is Anouk Bosman and I'm a PhD within PHOTONFOOD. I'm located at Wageningen University and Research. My research revolves around easy and portable sample preparation, which is the first and essential step in any analysis workflow.
So this is more or less the starting point of PHOTONFOOD. Here we can see two types of wheat. One non-contaminated wheat kernels, one type of kernels, and also we have here wheat kernels which show clear symptoms of Fusarium infection. You see decolorized samples and also you can see here pinkish samples which indicate the presence of Fusarium. And in a typical PHOTONFOOD workflow, what we will do now, we will get, for example, during harvest, the farmer can take a sample of these intact wheat kernels with the developments already present in the PHOTONFOOD project. With here our on-site sample handling prototype, which Anouk will now further elaborate on.
So once you've scooped in your kernels, we can attach this 3D printed prototype with each other. And once it's locked, you cannot detach it anymore. This also ensures user safety. So to make things easier, we wanted to make it automatic. So therefore we made a drill extension and then start grinding the kernels. Once this is done, you can look at your grind kernels, and then after that, I will show. So here you see the ground kernels that the device just did with the drill extension. And these kernels we can use to perform extraction. In extraction, you extract the compound of interest, so in this case our toxin. You extract it into a liquid, so that the liquid phase can be analyzed by the other prototypes of PHOTONFOOD. So therefore we use paper-based microfluidics. As an example, we put here a paper strip, and with this paper strip we pre-concentrate and enrich the toxin of interest in the paper tip, and then after that we can transfer it to the other devices and measure it.
So hello, this is my colleague Palina. I'm Tony. We both work together in Ulm University at the Institute of Analytical and Bioanalytical Chemistry.
Our aim in the PHOTONFOOD project is basically integrate all devices together. For example, infrared light sources developed by our partners NanoPlus, together with the ATR waveguides and detector and other optical components to build a compact, reliable and portable mid-fidelity and high-fidelity devices for the rapid mycotoxin analysis in field and on-site.
We are here at the Young Researchers meeting to demonstrate the performance of the Hi-Fi and the MiFi devices and interface them with the paper-based microfluidics developed by Wageningen University. This is the hi-fi device in which we have different parts. We have a light emitting source, which is the laser. Then we have two mirrors, which helps us for the aligning to point the laser beam. Then we have different components like this focusing lens, and we try to focus the light through the waveguide where the sample will be located. Then this light is collected by other optical components, which will be focused again to the detector, in which we will see the signal in our oscilloscope. The sample is located on the gallium arsenide waveguide, which has a thickness of 6 microns. The samples can be measured in liquid or solid state and will partially absorb the evanescent field produced by the laser light going through the waveguide. Then this difference will be recorded by the detector, which can measure the concentration of different components of our sample.
Our device has advantages over other methods because usually in the laboratory people use chromatographical methods of analysis, which requires quite big devices and also train staff to operate these devices. In our case, hi-fi device is a portable device which can be taken on site and could be operated by people who has not so many knowledges in the IR spectroscopy by just pressing the button and getting the results on the screen of the PC. In the first iterations where we were building the setup, we had the problem that the setup was a bit bigger than it is right now. Then our partners from Seeberge gave us an input that it could be nice that setup will be a shoebox size. So we spent quite some time on making the device more compact and portable so that it is ready to be suited in the suitcase and taken in the field.
Hello, my name is Valeria Tafintseva. I'm a researcher in data science at NMBU and leading the data science activities in PHOTONFOOD. The PHOTONFOOD devices use infrared electromagnetic radiation to detect specific molecules. Since the aim of the PHOTONFOOD project is to detect mycotoxin molecules, we use short spectral ranges in the infrared that are specific for the detection of mycotoxins. The goal of the NMBU team is to develop data analysis algorithms that can handle this special type of data. Infrared devices require calibration of the instruments. We calibrate the instruments against reference analysis for mycotoxins performed at BOKU. It's very important to have good and sufficient reference material. Reference material are foods where we know the exact mycotoxin content. These materials are measured with the new PHOTONFOOD devices, and the obtained data is then used with the known mycotoxin contents to train a model. This process is called calibration. The work with reference materials done at BOKU is therefore very important for the establishment of reliable calibration models. Calibration is done by machine learning algorithms. However, before the calibration is done, spectral data requires standardization. Our team is specializing in both standardization of spectral data and calibration modeling. Together with our partner IRIS, we integrate the new algorithms in a software interface for mobile and laptop to be used, for example, at farms, in food production, at food control authorities, or in the retail sector. Thank you.